Hello, curious minds. Today we are going to look into the fascinating world of atomic masses and why they're not always whole numbers. Let's take a look at this mystery together. So, first, if you guys remember what atomic mass is, you look on the periodic table and you find that atomic mass, and you'll notice that it's in decimals. But we talked about the fact that protons and neutrons have a mass of one atomic mass unit each, and electrons really don't have a mass. So, why is it that there are decimals? Well, what happens is we take an average mass of all of the isotopes of an element, and these elements usually have multiple isotopes with different masses. Some have two isotopes, some have three, some have six or seven isotopes, and so that's gonna create some different changes when you're looking at an average. Now, what's special about this is that we take a weighted average, okay, for this. Um, just a reminder, taking a look at isotopes, atoms of the same element with different number of neutrons are isotopes. The abundance of each isotope, or how many there are, affects the overall atomic mass. The more abundant an isotope is, the more it contributes to the mass. And we'll see kind of how that works as we go through a calculation, as a matter of fact. Let's try a calculation here. So there are three isotopes of carbon 12, or of carbon. They are carbon 12, carbon 13, and carbon 14. So carbon 12 has six protons and six neutrons, which gives it a mass of 12. That's why we call it carbon 12. Carbon 13 has six protons and seven neutrons, giving it a mass of 13, which is why we call that carbon 13. Carbon 14, there is not very much of it out in the wild. But it's something that we talk about often when we're dating things. Okay. So carbon 14, six protons still, but now it's got eight neutrons. Okay. Giving it a mass of 14. Now, what happens is in the abundance or how many there are of each of them, 98.89% of all of the carbon that we find in nature is carbon 12. 1.11% of all the carbon that we find in nature is carbon 13. And then carbon 14 is way less. It's so small. It's too small. It doesn't really affect our numbers. So we're going to focus just on carbon 12 and carbon 14. So we talked about the fact that carbon 12 really has a mass of 12 AMUs, or 12 atomic mass units, um, because of the six protons and the six neutrons. But that makes up 98.89% of all the carbon. So when we do an average, we do what's called a weighted average. So we're going to take that 12 times the 98 up. I noticed that I just messed that up. It should be 98.89. That's the percent. Multiply those two together and add to it my carbon 13, the mass of 13 AMUs, times the 1.11% down here. Okay. If I add those two values together, I get 1,201.11. Since it is a percent, I'm dividing the whole thing by 100, and I end up with 12.011 AMU. And if you look at the periodic table, you will notice that uh, carbon has a mass of 12.011 AMUs on your periodic table, or awfully close to that. So let's try it. Take a look at another one here. Taking a look at neon. Neon this time actually does have three isotopes that we're going to look at. Again, changing the number of neutrons changes the mass. So neon 20 has a mass of 20, which makes up 90%, a little over 90% of all the neon that we find. Neon 21, okay, mass of 21 makes up 0.27%, still enough that we're gonna count it. And then neon 22 has a mass of 22, and there's 9.25% of all neon is that neon 22 has that mass. So doing the same thing, taking our mass of 20, multiplying it by 90.48% for the first one, our mass of 21, multiplying it by our 0.27 for the second one, and then the third one, so this is 1, that's 2, and this is 3, is our mass of 22, multiplying it by the 9.25%. We take all of those numbers, add them together, and we end up with 20.18 8 AMUs for neon. Awfully close to what's on the periodic table. So the decimal values on the periodic table reflect the weighted average of isotopes. So now let's take a look at the worksheet that goes along with this and see how you guys do putting this together.